Okay, this is for Calculus 3, and this will be the instruction video for 14.3, which is about partial derivatives. So let me go ahead and share my note screen here. Okay. So partial derivatives, we were introduced to this back in brief calc, if you took brief calc before AP Calc BC. And it's just the idea that when you have a variable that has more than one input variable in the domain, then you can take the derivative of how quickly the output is changing with respect to either of the variables independently. So in regular calculus, when we have y as a function of x, single variable, right, the derivative is the slope of the tangent line, gives the instant radius change of the curve. So if you do a change in the x direction, right, then it produces a change in the y, and that derivative dy dx is basically an instantaneous slope for the curve, right? But what would derivative mean for something where we have a domain that's two-dimensional and we have an output variable as a function of the two input dimensions, right? Because now you could go in different directions, and how fast y is or z is going up or down is going to depend on, well, what direction are we changing? Are we changing just in x, just in y, or some combination? Okay, so at first, we restrict ourselves to only changing in the direction of the coordinate variables. So just x and just y. Later, we'll define more general directional derivatives, but for now, we define this. We say if we hold x constant on some plane, let's say, for example, x equals 6, then we can vary y. So we have a change in the y direction, and that will produce a change in the z direction. Okay, but to indicate that that doesn't, it's not telling me the complete story, I'm going to use different symbols for this. But basically the idea is we're going to hold one of the variables, the input variables, constant, and allow only the other one to vary. And so the x would be held constant, right? That's one derivative, okay? But we could also decide to go to a particular value of y and hold y constant, right? So we're defined it like maybe on the plane y equals 8 here, allow there to be a change in the x direction, and then note what the change in z direction will be. So what's the change in z direction per change in the z direction, or x direction, right? And so these two derivatives, dz dy and dz dx here, are partial derivatives. But to indicate that they don't tell the full story, we use a different symbol. Instead of the regular d, we use this symbol here, which people use different words. Sometimes people call it di-z. I like to call it del-z, but there's no official name for it. A curly d, sometimes people call it curly d, and it's not even really a Greek letter. It's its own thing. So it's kind of like a d. I just draw it like that. It's like a d that's sort of weird with a curly tail. So curly d, z, curly d, y. I'll probably just call it del-z, del-y, or dz, dy. This means that we're going to differentiate the output f or z, but with respect to y, treating that as the variable while holding the all other variables constant. So if there's any other input variables other than y, so this is the variable we're varying, and then we're seeing how the output changes, all other variables are held constant, okay? And the two symbols for it are, there's this del notation, so del z, del y, but there's also, you can put f with a y down here. So a subscript of a y indicates you're taking the derivative. So it's like f prime, but we can't really just stick with prime because there's multiple directions, right? Well, what directions? So this symbol means f prime, except where the variable that we're allowing to vary is in the y direction, and all other variables, like x in this case, are held constant. Right? If we want to go the other direction, that would be dz dx, right? Which is written fx because x is the thing that's being allowed to vary and y is being treated as a constant. Okay? So computationally, what you do is you just treat all variables as constants except for the one that you're allowing to vary. So let's say we have a function where an output variable z is defined in terms of two input variables x and y. This symbol fx means to allow x to be the variable, right? And everything else is treated as if it was a constant. So the way I do it is I underline what the variable is. So there's the x here, and there's an x here, and we're only going to take the derivative of that. Okay, so like for this term here, the derivative would be 3x squared. This term has no x, so this whole thing is just a constant, and therefore its derivative is 0. And this one has an x, but times a -3 and a y squared, okay? Now, normally you would think, oh, I have to do product rule. But in this case, no, because we're going to treat this y squared as if it was a constant. I'm going to think of this as the constant -3y squared times the variable x. And that means the derivative is the 1 just times this constant. So it's the constant -3y squared times the derivative of x, which is 1. So only the x's participate in the derivative, just this and this. In fact, when I really do it, for this one, I would just take, okay, what's the derivative of x? That's 1, and then I would just multiply by everything else that was in the term. So this result ends up being 3x squared minus 3y squared. Okay, and then for fy, we're treating y as the variable. So that means the x is going to be considered a constant, right? So let me go back up here and erase this. And just let me underline what it is that is the variable. The variable now is the y. So this whole thing is just a constant, so the derivative of that is 0. The derivative here would be, the derivative here is 2y times the extra 2 gives me 4y. And then the derivative here is 2y, and then times 3x would be, let me write that in 2 steps. There's 3x, and then there's the derivative part there, right? So this actually would be 4y minus 6xy, okay? So f sub y is the derivative, the partial derivative of f in the y direction. Okay. And then if I were to plug some points in for x and y, I could evaluate what those are. So for this fx, if I plug 5 in for x and 5 in for y, I get 3 times 5 squared minus 3 times 5 squared, which turns out to be 0. But if I plug that into the fy, I get 4 times 5 minus 6 times 5 times 5, which turns out to be negative 130. Okay, so what does this mean geometrically? It means if I go out to this point, 5, 5, somewhere out here, let's say, exactly where it is, let's say it's here, okay? The fact that the x derivative was 0 means that if I go in the direction of the positive x-axis, the surface at that location is going neither up nor down, right? So the slope of this line is up or down 0 for every 1 unit in the x direction. But the fact that this one turned out to be negative 130 means if I go in the y direction, in the positive y direction, this goes down 130 units for every 1 unit over. So this is an extremely steep slope in the y direction, right? So I can separate the direction in the x from the direction in the y, and then figure out what is the output doing for every unit change in the x direction, and what's the output doing for every change in the unit y direction, per unit in the y direction. All right, and later we'll talk about how we can put those together to go in any direction, but right now we're sticking just with the x and y direction, okay? Okay, so you can pause the video and try that. See if you can just compute these things real quick, and then unpause and check. Okay, so let me work this too. Here's the function that's given. If I wanted to evaluate fx at any xy, the derivative here would be, okay, I've got the constant, and then that is a variable, so I do the derivative. This whole thing is a constant, so the derivative is 0, and that would be 2x. So this is actually going to be 6x squared plus 2x, right? And then for the y direction, actually, let me make a little space here. The y direction, let's see, this whole thing is a constant, so that's 0. I have 3, and then the derivative of the y part, which is the variable, is 1, and then that whole thing is a constant, so we just get negative 3, right? And so then if I wanted to evaluate these at particular points, like they said fx at 2, negative 1, when x is 2, y is negative 1, I'm just going to plug in 2 for the x, and this one requires another x, right, because there was no y, right? So wait a second, did I do that wrong here? No, that's right. So I have it wrong in my notes for some reason. Yeah, I have to plug in an x, so again, it's a 2. And so this would be 6 times 4 plus 4, so 28. I think my answer key says 22. I'll post it online for the filled in notes, but it's actually 28. Okay. And then for the individual, the partial derivative with respect to y evaluated at a particular value, like -2, 3, we would take this and plug in -2 for all x's and 3's for y's, but in this case there is no place to plug in, so it's just -3. All right? All right. Okay, so that is called the first partial derivative, just like the first derivative, but we can now specify which variable we're treating as a variable. Everything else is held constant. We can also have higher order partial derivatives. These ones are called first order partial derivatives. But if you take them and you get a function, you can take a derivative of the derivative to get a second derivative, right? So if we started by taking a derivative of something with respect to x, so we did fx, and then we took the result and we took the derivative again with respect to x, treating the x as the variable, that would be the second derivative. So the second order derivative fxx. And it means that you'd first take the derivative of the z function with respect to x, and then you'd take the result and take the derivative again with respect to x. So another symbol for this is del squared z, del x squared. And you can do the same thing with y. So fyy is del squared z, del y squared. But you could also mix things up. You could say, okay, let's start with taking the derivative with respect to x, and then when we get our function, that function could include y's. Then let's switch to taking the derivative with respect to y. That's written fxy, which means first we take the derivative with respect to x, and then we take the result and take the derivative of that with respect to y. So that's written del squared z, del y, del x. And if you have fyx, it means you take the derivative with respect to y first, and then the resulting equation you differentiate with respect to x, so that would be xy. So in terms of order, one thing to know is if you have fyx, it means you're doing the y derivative first, then the x. But if it's written in this form, it's actually reversed. This is the first derivative you take, and then the second derivative is that one. Right? Computationally, it's just derivatives of derivatives, and those derivatives might get simpler or they might get more complicated or stay roughly the same depending on the nature of the function. Okay, so what is the interpretation of the second partial derivatives? Well, we know from regular single variable calculus that the second derivative relates to curvature. It's the concavity, right? So it makes sense that at least some of these second partial derivatives would be concavity, and they are. So if you look at the ones that are xx or yy, right, fxx is the second derivative with x as always the variable. And that means we're always staying on a constant plane in the y direction. So if you had some surface like this, and you took fx, right? And that would give you the slope as you changed in the y direction. So maybe you'd have like +3 as the slope. These yellow numbers are the slopes. So +3 here, +2, +1, 0, and the slope becomes negative. Then if I take the derivative again with respect to x, that means as I'm changing x here, how fast are the slopes changing? So these slopes are getting more negative, right? And so there's a negative second derivative here, right? And negative second derivative is associated with concave down, right? But in this case, because we're differentiating with respect to x, it's concave down when we move in the x direction. So this does mean concavity, but concavity in a specific direction, right? Okay, and the same thing is true for fyy, except that it's in the changing in the y direction. So if you happen to have, a curve like this, right, then you could see. So these first things would be fy. What's the slope as you move in the y direction? +2, +1, 0, -1, -2, -1, 0, 1. And then if you take the derivative again with respect to the y, that's how fast the derivatives are changing. So, right, these are getting more negative here. Right, but then here it switches to becoming positive, and so part of this curve has concave down behavior, and part of this curve has concave up behavior. So just like with a single variable function, right, negative second derivatives are concave down and positive second derivatives, and you could have a function where for some of the y values it's concave down, and for other values it's concave up. And as you might imagine, whenever it's 0, that's when we're at a max or a min. So we're going to do a later section on optimization, and we're going to be finding, part of that procedure will be finding where these partial derivatives are equal to 0, the first partial derivatives. So what about the mixed derivatives, fyx? So I've tried to figure out, this is my own thoughts, this isn't in the book, but I think this is valid here. So fyx So first of all, Fy, that would mean as you're moving in the y direction, this is giving us the slope. So these yellow lines, these slopes, like we're at slope of negative 1.5, negative 1, negative 0.50, right? And then if we move if we take the derivative of that in the y direction, it means how are these slopes changing numerically as you move in the other direction? And since these are getting more negative, right? That means that they're decreasing, right? Well, it means that the slope is not staying constant, and that means that the surface is twisting, right? So I believe what this means is it's the rate of change that the surface is twisting. So if you have a high Fyx, second partial derivative, then that means that the surface is twisting rapidly. Right? And if you have like a 0, 1, it means that it's not twisting at all, right? All right. So this particular one would be something like negative 0.5 because the slope is changing, getting a half of a unit more negative. The slopes are dropping by 0.5 units for every 1 unit you move in the other direction, right? So kind of like twisting, right? Same thing in the other direction for Fxy, okay? So not official to know that, but I actually think it's kind of interesting that those, so the Fxx and the Fyy definitely correspond to concavity, but the mixed derivatives correspond to twisting. All right, so there actually is something called Clairaut's theorem that says, suppose f is defined on a disk D that contains the point AB. If the functions fxy and fyx are both continuous on D, then it does turn out that fxy and fyx, those two mixed partial derivatives, will always be equal, okay? So this one is actually not even proved in the textbook, so we just accept that as proven. The interpretation, if our interpretations are correct, what that kind of means that if you have a surface that's twisting, the second partial derivative as you move in the x and y direction have to be the same, because those are connected surfaces. It's one surface, so it can't twist in one direction one way and change to twisting a different direction the other way. At least not abruptly, not with it at a single xy location. Anyway, when you compute the mixed derivatives, you really only have to compute one of them because the other one is always the same. As long as you have a fairly normal function, as long as you have f is defined on a disk. If you have major discontinuities where this statement isn't true, then you can have weirdness here, but we're not going to encounter anything like that in this class. All right, so more examples. You could go ahead and pause the video and then unpause and see if you can find these second partial derivatives correctly. And I'll show you the work for these. Okay, so let's say we wanted to find fxx. First of all, we have to find fx. So that's the first partial derivative in the x direction. Treating x as the variable, I'll go a little faster here. This is going to be, let's see, 3. So that's going to be 6x squared. That's a constant, and this will be 2x. And then for the y, fy, is going to be, that's a constant, so the derivative is 0. This would be negative 3. Okay. And then if I wanted to do second partial derivatives, if I did fxx, I'm taking this function and taking the derivative over again treating x as the variable. So that's going to be 12x plus 2. And if I do fxy, that's going to be, let's see, well, there's no y here, so that's 0. And there's no y here, so the derivative is 0, so that would be 0. Okay, and if we do fyy, right, that's going to be, well, the derivative of that is 0. So that would be 0. And if I did fyx, that's also a constant, so that will be 0. And sure enough, Clairaut's theorem is true that the two mixed derivatives are the same. Okay. All right, here's another example. Now in this case, we added another variable. So just to show that this is true, no matter how many input variables you always have one output variable. So you can take the derivative of the output variable with respect to the other variables. Now, in this case, z has become an input variable, right? So I wouldn't be able to say dz dx anymore, right? I would have to have something like dw dx because I have to allow for a w dy and a dw dz. So I can't use z as my letter, right? Okay, but I'm going to stick with this notation, just f with the derivative with respect to x, but y. But now z is also an input function. All right, so let's take a look at it. You can pause the video and give this a try as well. So fx, this is all one big term. The only thing here that is a variable is this x. Everything else is to be considered a constant. So that means this portion is sort of like taking the derivative of e to the ax, right? Which means that I would say it's the copy times the derivative of the ax by the chain rule, which is going to be the copy times the constant. So it's going to be a e to the x, right? So same thing here, but my y at this point while I'm working with x as a variable is considered a constant. So first of all, the derivative of this would be, let me get rid of that, write all over it. The derivative of that part there containing the variable would be e to the xy. That's a copy, but because this wasn't just the variable x, we have to multiply by the derivative of what's inside the e to the x, which is y. And then the natural log of z just tags along because that's a constant. So this would be the fx. Okay, for fy, this also contains the variable. So the derivative of the e to the xy would be the copy, but times the derivative of this inside, this time with respect to x. You know what? Let me show that explicitly. So what I'm doing here is I'm taking the partial derivative of something with respect to y, and that's of this little function here. This natural log of z is still tagging along. So, right, the derivative of this part is e to the xy, but the derivative of the inside is now taken with respect to y. And so we've got e to the xy, and then this will just be, the derivative is now 1, so this is x, natural log of x. And then for fz, all of this other stuff is a constant now, and we're taking the derivative of this part. Well, so we have e to the xy hanging out as a constant, and the derivative of log is 1 over the input. So these would be the three partial derivatives here. Okay? All right. Next is a contour map given for a function f. Use it to estimate fx at 2, 1 and fy at 2, 1. So if I go to 2, 1, that's here. Fx means if I were to go 1 unit in the x direction, what would happen to the output value? So the output value right here is approximately 10, right? So while I'm evaluating x, we're going from f equals 10 to, if I go 1 unit, that'd be from 2 to 3. If I go 1 unit over to here, I guess that's somewhere a little bit less than 14, maybe like 13.8. I would say f is going to about 13.8. And so that means that the change in output is about, so the delta f is 13.8 minus 10. So I'm thinking this is around 3.8. And in fact, that would be, it's the change for 1 unit change in x. So that's an estimate of that. In fact, you can kind of think of it, maybe it'd be better for me to actually write it as a slope, right? Maybe that might be a little clearer. Fx, yeah, this is probably a better way to write it. What if I said, okay, so fx is basically the change in f over the change in x, and we're going 1 unit in x. So I'm going from 2 to 1, and then the output goes from 10 to 13.8. So I end up getting 3.8 over 1, or 3.8. Okay, and then for fy, let me use a different color. Fy would be change in f per unit change in y. So again, if I go up by 1, this is, let's see, this is 1, 2, 3. So yeah, this would be 1 unit to go from 2 to, or from 1 to 2. So if I go from 1 to 2, change in y, then the output goes from around 10 at the start. And at the end, this has become a little bit less than 8, maybe not quite to 7, but maybe like 7.2, something like that. It's somewhere between 6 and 8, right? If I kind of go along here, and we're right at this point. So I'm thinking it's 7.2, 7.5, something like that. Maybe we use 7.5 just to make it easier. So 7.5 minus 10 would be negative 2.5 over 1, so negative 2.5. So if we go in the x direction, the function value is increasing. If we go in the y direction, the function value is decreasing, has a negative partial derivative. Okay? Okay, here's one with a table given. It says the wave heights h in the open sea depend on the speed v of the wind and the length of time t the wind has been blowing at that speed. Values of the function height as a function of wind speed and time are recorded in this table. All right, so the t variable is up here and the v variable is here, and these are wave heights. What are the meanings of the partial derivative d? So what does dh del v mean? So this means as for every additional increase in wind speed of 1 knot, how much higher or less high does the wave height become? So I would just write that. I would say that it's equivalent to saying how fast is the wave height changing. Yeah, it's like per unit. Maybe we could say it's a rate of change. So it's a rate of change of the heights of the waves as we change the wind speed. So how fast does wave height change with changes in wind speed? That's the meaning of that. It really means for roughly 1 additional knot in wind speed, right, the wave height changes a certain amount. Okay, and then dHdt, partial derivatives, would be how fast does wave height change with changes in duration, right? The wind is blowing for a certain amount of hours, right? So for every additional hour that the wind has been blowing, how does the wave height respond? How fast is its height changing? And then for part B, it asks us to estimate values. So let's look at that. Estimating the values of FV at 40, 15. So we're going to go to 40 in the V, so 40 in the V, and 15, so it's this point right here, and we want to evaluate FV. So we're going to change in the V direction. That's this. So we're basically going to go, is this the right place? 40. Nope, I have that reversed. This is the V and this is the T. So we need to go to V. This is the V. This is the T. We need to go to V is 40. T is 15. Here's the spot. Okay. And then we want to increase in the direction of V increasing. So if I go to the next spot here, this would be VF or FV. So let me just estimate that by just taking the change in the output value over the change in the input value from 50 back to 40. Right? And that's going to be 11 over 10, or approximately 1.1. So basically it's 1.1, I don't know, what is the units for the wave heights, like feet, 1.1 additional feet in wave height per additional knot of wind speed. Okay, and then the other one was FT. So FT at the same location means we're going to move in the T direction. So that's going to be 28 minus 25, and then 20 minus 15. So this will be an increase in 3 in the wave height for a change of 5 hours, right? 5 hours. So 3/5 would be 0.6. So on a per unit basis, the wave height is a little more sensitive to the speed of the wind than the duration of the wind. Okay. What are the practical interpretations of the values? I would say basically just that there's a bigger change in wave height if I change wind speed than if I change the duration that the wind is blowing. Okay, and then for part C, it says, what appears to be the value of the following limit as t approaches infinity of partial derivative of h with respect to time. So wave height as I move with time. Okay, so if we move with time and we allow this time to go to infinity all the way across this table, right, what's happening to this little change in h versus change in time, right? So like let's pick one of these rows. We'll do this one, for example. So I would have a change here of 1, right? And then here it would be a change of 1, and then another change of 1, but then it becomes a change of 0. And as I look across here, right, the changes appear to be approaching 0, right? They start out bigger, but then they get smaller and smaller. So I would say that that limit is equal to 0, right? In the limit, it appears that it's approaching 0. Right, which basically means that at a certain wind speed, after a while, it doesn't really matter how long it's blown, the waves are only going to get so tall, and then they're going to not change anymore. Okay? All right. Find the first partial, this is the last example, find the first partial derivative of this. Okay, so this is kind of weird. We want fx and fy partial derivatives. So let's look at fx. So fx is going to be the partial derivative with respect to x of this thing, which itself is an antiderivative. So we're taking a derivative of an antiderivative. And those are going to cancel each other out. In fact, this is going to just leave me with cosine. Okay, but the constant of integration here is t, not x or y, right? But while I'm taking x as treating that as the variable, it means that this is effectively a constant. It's almost like having an a. And if you remember from way back when, the fundamental theorem of calculus says this. Fundamental theorem of calculus part 1. It says that, you know, if you're taking an antiderivative from a constant to x of a function with respect to another variable, that's going to give you the antiderivative, but with this x plugged in, f of x. Okay, so in this case, I'm then undoing this with a partial derivative, and so I'm going to get the original function again, except with whichever thing is the variable plugged in. So by the fundamental theorem of calculus, this is just since the y is being held constant, the variable here is x, and this would just be therefore x squared. Okay, kind of convoluted. I think that might be one of the homework problems, and that's the reason why we include that. But if we did fy, then I'm taking the partial derivative with respect to y of this function, right? And now it's the x that is the constant, right? So this is the constant. So what would that look like? Well, this would normally be just the cosine then of the y squared. However, this is in the wrong form, right? The fundamental theorem has the constant here and then the variable up here. So what happens if instead of doing that, a function with respect to t, what if we reverse these and do the constant here? Well, whenever we reverse, there's a property that says that gives you the negative. Right, and the reason for that is because ultimately it's an antiderivative, and if I reverse these two, if I make it a minus b, that's the same as the negative of b minus a. Right, so there's a property that says you just take the negative. So in fact, if I do the partial derivative of the y, because the constant's in the wrong spot, the variable here, it would be the negative of cosine of y squared. Okay. Not at all intuitively obvious, so I thought that would be worth mentioning. All right, that's it for 14.3. So go ahead and give the 14.3 homework a try then, and bring questions to either class or to tutoring.